Operational amplifiers are the building blocks of analog electronics, but their theoretical ideal rarely matches the messy reality of physical circuits. In this section, we examine the practical limitations that engineers must account for when designing with real world hardware. When designing with operational amplifiers, we must balance theoretical ideals against physical realities. The ideal model assumes infinite impedance, zero output resistance, and perfect gain. In practice, these metrics are limited by silicon properties, requiring careful compensation for real world precision. The ghost in the machine is output offset, a subtle error that persists even when the system is supposedly at rest. This diagram illustrates the underlying physics. Internal transistor mismatches generate a small input offset voltage, which is then amplified into a noticeable output error. Because these errors can compromise precision, understanding and calibrating for this offset is critical for high fidelity electronic systems. What is the ideal value for output impedance in an operational amplifier? High impedance is bad for output stages. Unity refers to gain, not impedance. Correct. Zero impedance allows the op-amp to drive loads without voltage drops. In signal processing, distinguishing between differential and common mode signals is fundamental. Differential mode represents the useful information, while common mode often acts as interference. Our goal is to maximize the common mode rejection ratio, or CMRR, to ensure sensor accuracy. When analyzing op-amps, we focus on small signal bandwidth characteristics. The open loop gain response reveals critical performance limitations. Remember that gain and bandwidth always operate in a strict inverse trade-off. When we push an op-amp to its limits, we encounter slew rate, which dictates how quickly the output voltage can change. This leads to several critical design considerations for high-speed applications. Understanding this transition from square to triangle waves is essential for maintaining signal integrity in audio and power circuits. If an op-amp has a GBW of 1 MHz, what is the maximum gain possible at a frequency of 100 kHz? The UA741 serves as the foundational example in electronic circuit design. Let's review the cost specifications of this classic operational amplifier. While considered slow by today's standards, its ubiquity makes it an essential tool for educational purposes, innovating the architecture of the future. These foundational steps ensure scalability and precision for everything that follows